Newton's laws of motion. In the past week, we have been discussing about the motion, including the quantities involved in describing an object's motion, but we haven't studied yet the quantity that caused motion. In this chapter, we will be learning about the forces that cause the motion and the laws that govern them in classical scale. Shown here are some of our daily encounters of force. By now, it is also important for us to be aware that forces is not limited to the push and pull that cause motion into macroscopic objects. We also have the action at a distance force that do not require direct contact for force to be exerted, and these forces include magnetic force, the electric force, and the gravitational force. So far, we had deal with describing motion caused by some contact forces and the gravitational force. We know already that force is a vector quantity, which means that it has magnitude and direction. For convention, we denote force by letter F, and it has a standard unit of newtons or N, by which 1 newton is equal to 1 kilogram per meters second, 1 kilogram meters per second squared. And since force is a vector, if several forces are acting on an object, the total net amount of force acting on that object is just the vector sum of these forces, as shown here in the figure. To make it easier for us to add force vectors and eventually be able to determine the net force that is effectively acting on the object, we need to learn and master first how to make a free body diagram or FBD. Creating a free body diagram is a technique used to simplify any physics problem. Here, the object is represented by a point which is at the center of mass or center of gravity, while the force is indicated as arrows with lengths of lines indicating the magnitude of the, fo- the force and the head pointing towards the force direction. In other words, FBD are used to show the relative magnitude and direction of all forces acting upon an object in a given situation. For example, this box being pulled by the person. What we see is this person pulling the box, and as a result, the box is now moving towards the right, and here it seems to be heavy, so this person is having a hard time moving the box. By observing this, you may see, okay, this person is acting a force on this box and is now moving towards the right. So if we create a free body diagram of this situation based on the definition of the FBD, it could be easy. Let we let the box be represented by a point here as shown here, and then draw an arrow going to the right and call it a day. But unfortunately, this free body diagram here is wrong. So there are very important components here that is missing, and what we should see instead is this one. So this is the correct free body diagram. So the free body diagram includes all forces acting on the box regardless if these forces are balanced out or those that are cancelled out by equal but opposite forces. So here, instead of just one force, the FBD tells us that there are actually four forces acting on the box. But how can we explain this? So the box is only moving to the right. What happens to the other three forces? If you look closely, we have a downward force denoted by vector W, and also we have an upward force denoted by N. We can also see that the lengths of these vectors are the same, which means that they have equal magnitude. Since they have opposite directions, these forces just cancel out when we get the net force. So thus justifying that why we do not observe vertical motion of this box. Lastly, we have vector force directed towards the left. This means that the net force exerted on the box is not completely equal to the amount of the force applied by this person. The net force must be lesser since this dragging force should be taken into account. Now that there are that these three forces, now what are these three forces really, and why are they all of a sudden appears in the FBD? To understand fully how to make the free body diagram, let me introduce you formally to these three forces. So the downward force shown in our previous FBD, or shown here in this slide also, is known as the weight, or the force that is due to the pull of gravity to anything that has mass. The normal force is the upward force, which is always normal to the surface, and in this case the surface is perpendicularly horizontal. So the length and the normal force, so the weight and the normal force are exactly opposite in direction, since they have the same magnitude and they cancel out. The friction, on the other hand, is known as the force that is always opposite to the direction of motion and therefore causes resistance. We also have this force applied by the person to the box. So by having this FBD, we can actually approximate the magnitude of the net force exerted on the box as well as the most probable direction of this motion. Let's learn more about these forces. So first we have the weight and the normal force. So weight, as what I have mentioned earlier, is a force due to gravity. It can be calculated by getting the product of the mass and the acceleration due to gravity, hence W equals mg. Here g is equal to 9.8 meters per second squared. Now, since weight is dependent on the Earth's gravity, that means our weight is not necessarily the same if we calculate or measure it in the outer space or any other planet. So it is the mass that is constant no matter where we wish to measure it. Normal force is referred to as the perpendicular force exerted by the surface to an object resting on it, and in a horizontal surface as shown in this example here, the normal force is equal to the magnitude of the object's weight but opposite in direction. The friction force, on the other hand, is a result of the physical contact between two forces. There are two types of friction force, the kinetic friction and the static friction. The kinetic friction, usually denoted by F sub k, is the friction associated with the object's motion. This type of friction resists the motion of the object. That means if the moving object is directed to the right, the kinetic friction is directed to the left. The kinetic friction is expressed as the product of the normal force and the coefficient of kinetic friction denoted by mu sub k, while static friction is the friction force associated with the objects at rest. In other words, this type of friction is responsible for the behavior of an object at rest to resist the tendency to be in motion. It is expressed as the product of the normal force and the coefficient of static force mu sub s. The coefficients of kinetic friction and static friction describe the property of different types of surfaces. Shown in this table are the corresponding coefficients of some common interface combinations. We have rubber on dry concrete, we have wood on wood, metal on wood, and so on. So what these values actually indicate. So given that friction generally opposes or resists the tendency to be in motion or the tendency to accelerate, we can say that the greater the values of these coefficients, the greater would be the values of friction force, and hence the harder it is to move an object at rest, as well as how the harder it is to keep a moving object in motion. Also, static friction is always equal or larger in value than the kinetic friction. So this explains why you need to exert a larger force to move an object from rest, while you only need lesser amount of force in keeping the object in motion or keeping it at constant velocity. Since we already introduced forces, it is now time to unify our knowledge about forces and the kinematics. So Sir Isaac Newton coined three laws which relate force to the quantities describing an object's motion. So first, we have the Newton's first law, which addresses two situations. So first, for the objects at rest, and second, for the objects in motion with constant velocity. So first, it states that an object at rest will remain at rest unless acted on by a force, particularly an unbalanced force. Suppose there is a box in the surface. So if we don't apply force in this ball, it will not move. That means the forces that are acting in this ball cancels out. In other words, they are all balanced forces. For example, the ball has mass of 10 kilograms. So to calculate the weight, we have mass times the acceleration due to gravity. Thus, the gravity exerts 98 newtons of downward force on the ball. When we say downward, it's always towards the center of the earth. So the force that the ground or the surface exert on the ball is the normal force, and the force and it is the force balancing the weight in order to keep the ball at rest. That means the normal force is also 98 newtons, but its direction is opposite to the weight force. Hence, the net force on the ball is equal to zero. Let's clarify that it does not mean that there are no forces exerted on the ball. There are forces acting on it, only that these forces are cancelled out, resulting to zero net force. Second, the Newton's first law also states that an object in motion will continue in motion unless acted on by an outside force. Shown in these animations are the motions of a ball in three different cases. So in the first case, the ball is in constant motion and no net force is acting on it, so the ball continues in motion. However, if the ball hits the wall exerts a net force into the ball, and this force is directed to the left, and eventually the, the ball is now stopped. If we have a rough surface like a carpet as shown in this third case, we roll the ball in this carpet, it is more likely to stop at some short distance. The reason why it happens is that even though the ball is in motion, there is a lot of friction between the ball and the surface of the carpet. Because there is now a net force, this ball come to rest. And that's what we see in real life. That means it is friction that causes the net force acting on this ball. What will happen if we get rid of motion? So will the ball continue to move in motion? So let's imagine that we use the same ball and we roll it on ice. So it's going to roll a very long time until it comes to rest. It will not really move to infinity because even though the ice offers less friction, it is not totally equal to zero, and we also have to take note of the effects of the air resistance, is also opposite to the direction of the moving object. The air molecules can slow down the object's motion, and we call it also the air drag. Well, in this case, where our motion is taking place, where yeah, in the case where our motion is taking place in the outer space, we can approximate the air resistance as equal to zero, and the reason for this is that the lesser density of molecules in the outer space. If we take into account now, uh, if we think about it, we know that Earth revolves around the sun. Hence, an object in motion will also know. Hence, an object in motion. So we also know that the Earth has been revolving around the sun for billions of years, and until now it keeps on moving. So as you can see, it makes sense because in the outer space, there is approximately no air drag, or it is very low. So that cannot slow down the Earth significantly. So it continues moving on its orbit. Thus, we can see there Newton's first law in action. Now, the Newton's first law of motion is also known as the statement of the law of inertia. So by definition, the inertia is the tendency of the object or the body to resist motion or changes in motion. It is important to remember that the greater the mass of an object, the greater is its inertia, hence the greater the force needed to accelerate it. So it is great knowing all of this information, and the concept itself is very interesting, but how can we actually apply this in solving problems? Well, we have to create or coin some equations based on this information. First, we know that when an object is at rest, all forces acting on it balances out. So the net force acting on it is equal to zero, or F net equals zero. Next, if the object is moving at constant velocity, then the net force acting on that object is equal to zero, which consequently means that the acceleration of this object in that direction is zero. Here, we keep in mind that acceleration is defined as the change in velocity divided by the change in time. So, if the net force of an object is not equal to zero, then there must be a net acceleration of this object. And that leads us to the Newton's second law, which states that the net force is equal to the product of the mass and acceleration. So if the acceleration is constant, and we increase the mass of the object, the net force will increase. In other words, the net force is proportional to the mass of the object. How can we illustrate that one? Well, suppose that we push two boxes. The other one is heavier than the other. Which of these boxes is harder to move? It is obvious that the heavier box or the heavier object is harder to move, which means that it requires greater amount of force. That's why we have the net force directly proportional to the mass of the object. Now, if we keep the mass constant and we increase the acceleration, the net force will still increase. Hence, the net force is directly proportional to both the mass and direction. Suppose that we keep the force constant. What will happen to the acceleration if we increase the mass? As you might have imagined, if we push two boxes with different masses and we use exactly the same amount of force, the heavier object will be moving slower. Also, if we decrease the mass, the acceleration increases. Given that, please answer uh, this assignment to check our comprehension, and I will send you the link of this assignment in the Google form. We can also express Newton's second law of motion in terms of different quantities. So to start, let's write F net equals ma. We know that the acceleration is the change in velocity divided by the change in time. So the F net equals the mass times the change in velocity over the change in time. Now, mass times velocity is known as the momentum, which usually indicated by letter P. Momentum is the mass in motion, so an object at rest has zero momentum and the object that is moving has non-zero momentum. Which which object has larger momentum? Let's say a car moving at 3 kilometers per second or per hour, or a train moving at 30 kilometers per hour. Well, based on this equation, the train, which has significantly larger mass compared to the car, has larger momentum even though they are moving in the same speed or velocity. In the case of two objects moving in the same velocity, the heavier object always has larger momentum, and likewise in two objects with equal masses, the one that has larger velocity has the larger momentum. You can imagine this by trying to stop these objects, no? We know that it is harder to stop a train than to stop a car. An object with a lot of mass and a lot of velocity has a lot of momentum, and consequently, any change in mass or any change in velocity, or both change in the mass and velocity, means a change in momentum. However, in our discussion in this subject, we will only focus on the change in the object's velocity. The cases where there are changes in mass are reserved for discussions in higher physics courses, particularly in classical mechanics. So you may meet them in your major, or if you plan to shift to BS physics courses. So to proceed, we have mass times change in velocity equals to the change in momentum, which is m delta v equals delta p, which is the numerator here in the expression for our net force. That means that our net force is equal to the rate of change of the momentum with respect to time. So this is another expression of the Newton's second law. The net force is equal to the change in momentum divided by the change in time. If we multiply both sides of this equation by delta t, we, we will get another important quantity, that is F delta t equals change in momentum. In the term in the left-hand side, which is the product of the force and the change in time, is known as the impulse, also defined as the change in momentum. This is known as the impulse-momentum theorem, which states that the change in momentum of an object equals the impulse applied to it. Newton's third law: for every action there is an equal and opposite reaction, that is, F sub A equals negative F sub B. That means whenever a body exerts a force on a second body, the second body exerts a force back on the first body that is equal in magnitude in and opposite in direction. Both forces will have exact the same magnitude, but their direction could be exact opposite of each other. To illustrate, suppose that you are a basketball player and you pass the ball to your teammate across the court. While throwing the ball, you exert a force on that ball equal to the mass of the ball times the acceleration of the ball going to, say, positive x-axis. But you will also notice that you're 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 doing what that while you are doing that, you slightly bounce back, like a recoil action applied to your body. That recoil force is known as the reaction, and the magnitude of this recoil force is equal to the force you applied on that ball that you have just thrown. But you might wonder how come that the ball have reached the position of your teammate, which is a distance significantly larger than the distance you have stepped back during the recoil. Well, you have to remember that the ball has significantly smaller mass than your body. That means the ball's acceleration will have to compensate for that amount of force. In your case, since you are significantly heavier than the ball, your acceleration will have to compensate, and that is, your acceleration should be significantly smaller compared to the acceleration of the ball, and that is the only possibility that the magnitude of the force you exerted in the ball and the magnitude of the force exerted by the ball into you will be equal. To make it clearer, suppose that the ball is 1 kilogram while you are 50 kilogram. If the acceleration of the ball due to the force you exerted is 10 meters per second squared, that means that your acceleration due to the force exerted by the ball is just 0.2 meters per second squared, and that is directed towards the opposite direction. Thus, the force you exerted to the ball is equal and opposite to the force exerted by the ball to you. Example, if we have the earth and in this side and the moon here, and suppose that you are an astronaut and you hold a ball in your hand, in which direction would you or should you throw the ball in order for you to get back to earth? If you throw the ball towards the moon, you are going to feel an opposite force pulling you away from the moon, which will bring you towards the earth. Since in the outer space there is very small friction, we can assume that you will be moving towards the earth unless any other forces will be exerted. So here's another example. Suppose a car travels on a road with constant velocity. What is the horizontal net force acting on the car? What is the acceleration of the car? If the friction force acting on the car is 50 newtons, what force is applied on the car by the engine? So first, by Newton's first law, we recall that at any time the object moves at constant velocity. That means that the net force is always equal to zero, and this object will continue to move in exactly the same constant velocity unless an unbalanced external force is exerted to this object. For letter B, now how about the acceleration of the car? Well, according to the Newton's second law, F net is equal to ma, and in letter A, we know that the net force is equal to zero. Since the mass of the car cannot be equal to zero, this means that the net force is equal to zero because the acceleration is equal to zero. We can even skip analyzing this using the Newton's second law and can automatically conclude that the car's acceleration is zero because the because of the constant velocity which is already mentioned in the problem. Now, what force is exerted by the engine to the car? We know that the friction is exerting 1,500 newtons and is directed always opposite to the direction of motion. Now the net force is zero, which means that the friction must be or must have been cancelled out or balanced out by the force exerted by the engine to the car. Therefore, the force exerted by the engine into the car is also 1,500 newtons, but it is directed towards the direction of the car's motion. Since these forces cancel out, the car continues to move with constant velocity. Another example, a force of 200 newtons is applied on 10 kilogram box across a frictionless surface. what is the acceleration of the box? And if the box accelerates from rest, what will its final speed be after 8 seconds? And C, how long will it take for the box to reach the speed of 500 meters per second if it continues to accelerate at this rate? In this case, the net force is just equal to the applied force. Hence, the applied force, um, 200 Newton divided by 10 kilogram gives the acceleration of 20 meters per second squared. If the acceleration is equal to 20 meters per second squared, find the speed after 8 seconds. So we can apply the final velocity. We can calculate the final velocity after 8 seconds by making use of the kinematics equation for the horizontal motion, especially this equation. So, in which we substitute the values of the initial velocity, the which is 0, the acceleration equal to 20 meters per second squared, and the time, which is 8 seconds. Thus, after 8 seconds, we can see here that the box is now moving at 160 meters per second. For letter C, if the final velocity, if the box continues to accelerate at this this acceleration, and we wanted to know how long it takes to reach the velocity of 500 meters per second. To do this, we just use the same kinematics equation, this one, and then we rearrange this equation to solve for t. That is, t equals the final velocity divided by the acceleration. So after 25 seconds, the box is already moving at a speed of 500 meters per second. In example 3, suppose that a force of 300 newtons is applied to move a 20 kilogram sofa across the room. The friction force acting on the base of the sofa is 200 newtons. A. What is the net force on the sofa? B. Calculate the acceleration of the sofa. And C. How far will the sofa travel after 10 seconds if it continues to accelerate at this rate starting from rest? For letter A, towards the right, we have the 300 newtons pushing the sofa. Uh, Towards the left, we have a frictional force that is dragging it. So given that the push is greater than the frictional force, we already know that the direction of the net force is the same as the direction of the push, which is towards the right. The net force is just the vector sum of these acting forces. That is, the net force is equal to the push, which is 300 newtons, since it is towards the direction of the motion, plus the frictional force of negative 200 newtons, which is negative since the direction of the force since the direction of the frictional force is opposite to the direction of motion. So we get a net force of positive 100 newtons, which is directed towards the right. Letter B, since we already have the net force, we can use the equation net force equals mass times acceleration to find the to find the acceleration. So here, the sofa is moving with acceleration of 5 meters per second squared. And lastly, we wanted to know the distance traveled by the sofa at 5 meters per second acceleration after 10 seconds. So to do that, we simply use this kinematics equation for horizontal motion here, and then where the initial velocity is equal to 0. So substituting the values here, this will give us 250 meters. So the sofa is going to travel 250 meters in after the 10 seconds. So please check these other examples for your reference. You might want to try solving these problems on your own in preparation for the exam, and the answers are provided so that you can identify if your solutions are correct or not. And here's another example which you can work or try by yourself. So here's a challenging example where the surface is no longer perfectly horizontal. So we have here an inclined plane. So suppose that a force of 300 newtons, I mean, yeah, so here, okay, so here, lastly, there is a more challenging version of the problem. So let's consider a skier on a slope shown in the figure. So here, let her total mass, including the equipment, be 60 kilograms. And so the unknown here is that what is here acceleration if the friction is negligible, and next what is her acceleration if the friction is known to be 45 newtons. So notice that her acceleration is parallel to the inclined plane. No, it's not going towards this direction, it's towards this direction. So it is parallel in this plane, and it is also not going in this direction. So also, what causes her acceleration here is just the force due to gravity, which we know is the weight force. Thus, the first thing to do here is to calculate for the different components of the weight force. So given that the plane is inclined 25 degrees, we can calculate for the component of the weight that is parallel to the plane and the component of the weight that is perpendicular to the plane. That is, the component of the weight that is parallel to the plane is just the magnitude of the weight, mass times acceleration due to gravity, times the sine of 25 degrees. On the other hand, the component of the weight that is perpendicular to the plane is just the magnitude of the weight, mass, times the acceleration due to gravity, times cosine 25 degrees. By Newton's second law, we know that the net force is equal to the mass times acceleration. So to calculate for the acceleration using that equation, we need to determine first the vector sum of all the forces acting on the skier. Here we must only consider those forces that are parallel to the inclined plane, since the motion of the skier is only along the parallel directions of this plane. Since there is no friction for letter A, the only force acting on the skier is the parallel component of the weight. So the net force on this case is just mass times acceleration due to gravity times the sine of 25 degrees. And by Newton's second law, this is just equal to the mass times the acceleration. So we calculate this by mass times acceleration and then rearrange to solve for the value of acceleration, which gives us acceleration equals to acceleration due to gravity times sine of 25 degrees, which equals to 4.14 meters per second squared. Now, in the presence of friction force, the net parallel force acting on the skier is just the vector sum of the parallel component of the weight and the friction force. Notice that the friction is indicated as minus or negative. This is because the direction of the friction force is always opposite to the direction of the motion, which you can notice is lower. And again, when we substitute this here to the second law of motion and solving for the acceleration, this will give us 3.39 meters per second squared, which you can notice is lower compared to the acceleration of the skier in a case where the friction is negligible. So, therefore, what the friction does is that it it decreases the acceleration of this skier. And shown here are the summary of what we have just discussed. So thank you so much and see you in the next topic.